见证你的发型。
是，多少钱 ？HDMI 去过？OK。
好，待会我们就会开始了哈。那在这之前，我先提醒参赛队伍，就是不可以使用网络，不可以录音，不可以摄影。那另外，不要在投影机前放置灯光物品，会损坏我们的投影机。好，现在1点30分，那现在我们准备开始我们的辩论赛哈。那我先来介绍，我是屏东大学刘代敏，那我来主持这一场的各位同学的那一个比赛。那我先来介绍我们的评审。那首先介绍的是阳明高中大学林俊良教授，教授好。那第二位是我们逢甲大学李英德教授。我们中正大学包建豪包教授，还有我们中正大学姚教授。那接下来我介绍我们的参赛队伍。那从我左手边开始，我们是9120实验中学实验中学。那再来是我们的Lighting 是高雄中学。那最后是我们的Passion 是建国中学。好，那我现在先请各参赛队伍介绍队伍成员。那从我左手边开始。
好，这位是蔡长恩，然后校内节目王金璇，然后我是庄昭敏。
我是曾一柏，然后这是郑一成，然后这是刘环杰，然后这是黄祥佑，然后吴少伟。
Dear judges and fellow competitors, I'm the leader of the Placian, Chen Xingwei, and this is Su Yuan, Xu Yiyou, Hong Shaokai, and Zhong Yangmin. Thank you.
Alright. Okay, so now We have 1 minute. The opponent challenges the reporter for the problem. 1 minute.
Laplacian would like to challenge problem number 14, balls on the membrane.
Reporter, you have 1 minute.
这里可以放声。那这样子这题现象要怎么播放？因为它这里有
你的电脑大声一点。
你的电脑。
可是我们用另外一台电脑，然后就是同时会显示出它的声音。
We will accept the challenge.
Okay.
All right, so now we have 5 minutes for preparation of the reporter.
to start my report.
Right, presentation of report, 12 minutes.
Okay, so I'm George Wong from team NAC 9120, and I'll be the reporter for question number 14 on member. Okay, so my outline, common statement, observation, video theory, and we'll do some experiment and discussion, and our conclusion. Common statement, when dropping a metal ball on a rubber membrane stretched over a plastic cup, a sound can be heard. Explain the origin of the sound and explain how its characteristics depend on relevant parameters. So first we will do some theoretical value and explanation about the sound, and then we will discuss about what parameters will affect the sound. Okay, so our observation video. So as you can see, we will hear the sound of the caused by the vibrating of the membrane once we drop the metal ball. Okay, so let's move into our theory. Sound. So there are a few characteristics of a sound. First is volume, which is related to the amplitude of the sound wave, and frequency, which is the number of waves that passes through a fixed point in a given amount of time. So the sound wave is a longitude wave, so which can be shown like this. Okay. So the origin of sound. The sound occurs when a ball collides with a membrane, and the ball will provide the energy for the membrane to vibrate, and the air pressure will be created when the membrane vibrates, and which will create the sound. Okay, let's move into our dynamic model. So when the ball drops onto the membrane, the ball will be affected by the tension of the membrane, which causes it to jump, rebound up. So here the tension is like this, and we can simulate it into a spring. So which we can have a spring constant K. The reason we believe in this simulation is because the displacement vertically of the membrane is actually very small. So we believe that we can make this assumption. Yes. Okay. So when the ball leaves the membrane will keep vibrating, and the vibration will make the sound appear. So the membrane will be affected by a drag force, and yes. Okay, so if the ball is on the membrane, so here we define this as a balance line here. So when the membrane is so there's two situations. First is when the membrane is under the balance line, and second is when the membrane is above the balance line. So then the mass of the ball is n, and the mass of the membrane is n prime. And by Newton's second law, we can get this differential equation when the ball is on the membrane and they are both under the balance line, which the ball will move with the membrane. So we can get our solution for this differential equation. And the frequency of sound caused by this will be here, which we will be coming back there on. Okay, so if the ball isn't on the membrane, so that's when the ball leaves the membrane, and then so once the ball is in the air, the membrane will vibrate like this. So let's say vibrate many times before the ball will touch a membrane again. So within this time period, the ball of the mass wouldn't affect its motion. So by Newton's second law, we only consider n prime, which is the mass of the membrane. And we can get this differential solution, and the frequency of sound will be here. And here A is the initial amplitude, K is the elastic coefficient we assume, and B will be a dynamic coefficient, and phi will be the phase angle at t equals 0. Okay, so the frequency of sound. Since the frequency of membrane vibration is much higher than the frequency of ball vibration, you can just calculate the frequency when the ball isn't on the membrane. The reason of this is because as I mentioned, the ball will only affect the motion when the ball is on the membrane. So that's when the ball and the membrane is under the balance line together. But actually, when the ball comes on the membrane, it bounces up and then it goes in the air. And at this time, the membrane will vibrate many times before the ball will touch it again, which causes it to go down again. So that's why we believe that the frequency of the membrane vibration is much more important than what the ball gives it. Yes, so later on we will calculate our frequency using this this equation derived when the ball is not on the membrane. Okay, the volume of sound. So this so when there is no drag force, okay, so we can get this equation of the x component, and then we can get the speed, and we can know that the amplitude, which will affect the volume of sound, will be related will be v0 over omega, and which we will come back to discuss why we choose our parameters that we do our experiment. So the volume will increase when drop height increase, as we see here. So when the drop height increase, V0 will increase, and then when the mass of the membrane increase, so when the mass of the membrane increase, omega will decrease. Okay, damping. So the membrane will be affected by a drag force. So it said damping in volume. But however, the frequency will stay the same, and the volume would so the volume will decrease, but the frequency will stay the same. So our parameters, we are going to do the drop height of the ball, which we can see that will affect. We'll see what it affects, and the mass of the ball. We'll see what it affects, and the tension of the membrane. Here, we did not quantify. We did not quantify what exactly the tension is, but we used four different tensions of the balloon and rubber we used. Okay. So this is our experimental setup. So we have this roller to measure the bounce time, to measure the bounce distance, and the ball, and the structure to hold the ball, and the membrane, and the container, and the microphone to collect our data. So we use Audacity to measure the frequency of the vibrating membrane, and the average of the first 5 bounces of each test is used to create a spectrum as our experiment data. So we use this graph, and then we try to go into FFT, and we can get our experimental results. Okay, so we'll be focusing on these following characteristics, as I mentioned. First the frequency, and then the volume of the sound. So height varied. So so as I mentioned, we'll be using this equation to discuss our sound. And so F is independent of height. So we expect that the frequency wouldn't change. However, A is dependent of height. So we expect that the volume will increase when the height increase, when the drop height increase, and which this is pretty reasonable because like the higher it drops, you can see it as a greater force, which should cause it to have a greater sound. Yes. Okay, so this is our experimental results. So for this one, the mass of the ball is approximately 2 grams. So we fix that, and we use the same membrane. Yes. And so the frequency. So the frequency here of the drop height, this is our results, and we believe that this difference is caused by the error because it's actually not that different. So this is 345 and 344.5, and this is 347. So it's actually pretty close. And height vary volume. So the mass of the ball, again, the same setup, and as the drop of height of the ball increase, we can easily see that the volume will increase. Okay, let's go to it. So increase in drop height will increase the total energy of the system because it has a greater potential energy at first, which will result in an increase in volume. However, the frequency will be the same, and that fits our expectations from our theory. Okay, next one. We're doing our mass varied experiment of the ball. So this one, the frequency. So F is independent of N. So the frequency won't change. And A is dependent of N here, so the volume will increase. This is our expectations. So therefore, we expect that the frequency will keep the same and the volume will increase when the mass of the ball increases, which is a similar idea. Again, if the drop height is the same, then the greater the ball of the mass is, it has a greater potential energy. So it's actually pretty similar to the one before. So here, the drop height of the ball is 0.5 cm, and then we use the same membrane. And here again, we can see that there isn't a rule or any much of a difference in the frequency, and this is mainly caused by the error of the measurement. And the volume, so we can see that the mass of the ball, as it increases, the volume will, as expected, go up. Okay, so in increase of volume increase the total energy of the system, which results in an increase in volume. However, the frequency will stay the same. That's our expectations. And last one, we are going to do our tension vary experiment. So here, so K will increase when tension increase. So like if the tension of the rubber, for example, if I stretch it wider and it will be hard, the tension will be harder, which we can simulate as the spring constant being bigger. So F is dependent of K here, so the frequency will increase. And besides the increase in membrane tension will provide a more effective system in energy transformation, which results in an increase of volume. The reason of this is you can think of a guitar string. So if you loosen the string and you play it, you wouldn't have any sound. But if you play it tight, you will have sound. Okay, so therefore expect the tension to increase, and the frequency to increase and the volume to increase. So as you can see, this is our frequency. The frequency will increase, and our volume will also increase. So our conclusion is that sound is being caused by a vibration of the membrane. The main purpose is just to trigger the motion, increase the drop height, won't change the frequency, bottom mass won't change the frequency, and tension of the membrane will increase the frequency, and the bottom mass, drop height, and tension will all increase the volume of the sound. Thank you.
Questions of the opponent to the reporter and answers of the reporter. 2 minutes.
Okay. For my first question, can you turn to page 4? And page 4.
The video.
I'm going to ask what is the material of the container? What kind of the container?
This one?
Yeah.
Plastic.
Or it's just a plastic, just like a container. So, and please turn to page 11. I want to ask what's the meaning of the ball will stick on the membrane.
So like it's not like this. So for example, if you have a membrane right here, okay. So when you have a ball, it drops down, right? So it will touch the membrane, and then it will go down with the membrane. So the membrane will go in, and then because of the tension, it will come up, and the ball will bounce up, and then the membrane will keep vibrating.
Oh,
so
you mean
yes.
this process and
Yes.
the ball will stick on it? Okay.
Yes.
So then could you turn to page 15? Is the graph your is the this graph is your experiment data?
No, this is a theory.
Oh, okay.
Yes.
It's a theory, right? Okay. Okay. Just finish.
Right. Preparation of the opponent. 3 minutes. The opponent takes the floor, maximum 4 minutes.
Okay, and usually it fails at first, and the opponent from team doesn't. And for the public statement, when dropping metal ball on the rubber membrane stack over plastic cup, a sound can be heard. Explain the origin of this sound and explore how its frequency depends on relevant parameters. And I think that the focus of the problem is that the origin of the sound and the relevant parameters. Okay, so I want to summary. I want to summarize the reporter. And the reporter said about their theory, they use a damping harmonic function and use some differential equation. And their conclusion is that height affects the amplitude and tension affect frequency, and sound comes from the membrane, and the mass doesn't affect a lot of things. Okay. And for pros and cons, I think the reporter has many parameters and provide intuitive explanation of the phenomena, and will construct the presentation. And for cons, their theory is unpersuasive and did not measure the tension. Did not tell the way to measure tension and provide an unpersuasive explanation. Okay, sorry. And risky time management about your presentation. Okay, so the point I want to discuss with the reporter is first is about the experiment. I want to ask, how did you measure the tension and how to make a surface tension evenly distributed? And about the frequency spectrum and the container. And some interesting point I want to discuss is the vibration from the chamber and horizontally organic wave. And about your theory modification, I want to discuss some resultness and some frequency about the frequency spectrum. Okay, so I would like to start the discuss. Okay, could you answer me my first question?
How did I measure tension?
Yeah.
We didn't quantify our tension, so we didn't actually measure the numerical tension. But however, the way we did this experiment is, so we bought the same balloons and then we stretch it with the different force and then cover the same cup. So and we use a new balloon each time of the experiment. And then so we have like the least tense and the most tense.
So yes. You doesn't measure
yes.
Tension.
But if you want to measure tension, I believe that the dyne test pen is a great way to measure
I agree with you. And about your frequency spectrum, can you turn to yes, there is shows the graph of this piece. Spectrum. Okay, yeah. I want to ask is at this part, I want to ask why does the lower frequency will depth?
You mean this one?
Amplitude. No.
Where? This one?
Yeah.
Could you repeat your question?
I want to ask you why. Can you explain it?
So like okay. So this is only a demonstration. First of all, this is only a demonstration, and then the way we got our data is by like when we measure the sound. it will be like this, right? So it will be 1, and then 2, and then 3, and 4, and then we categorize each point. So it's like, so it will be like this, and then we get this point, and then so and then we.
Have you do you have the spectrum of your data? I want to.
Just on data.
Yeah. Spectrum.
Not, it's not on the PowerPoint.
Oh.
Yes.
Okay. And I want to discuss the vibration from the chamber. And the problem statement says ask us to find the origin of the sound. And I think, except for the membrane, I think the chamber will also vibrate. And I want to ask some idea.
Do you mean the plastic cup itself will vibrate?
Because the problem statement just point out you should use the plastic cup.
Yes.
To conduct it.
So I have a clarification question. So do you mean like if there's a cup and so I have a membrane on it? So do you mean the cup itself will vibrate and then the cup will cause sound?
I think for my view, I think when you drop the ball and the ball will hit the membrane.
Yes.
Okay, and membrane will stretch.
Yes.
Right, and they will. I think the chamber will also vibrate. Just like a membrane. So I think. I just think I think you can also analyze about chamber.
So if you're saying the vibration like this, then I think that wouldn't matter because
no, I say
just chamber.
Just vibrate like a membrane.
Yes. But you do realize that membrane itself it's very easy to change its shape, and the cup is not, right?
It's like plastic cup, I think.
But it has some thickness. But I do agree that if the plastic cup is
not a rigid,
thin,
right? So you will
yes,
vibrate.
but
Okay, so you agree with me. Okay, and I want to discuss the horizontal wave and let's come to the floor. Okay. And when your ball falls on the membrane,
yes.
right? And in your presentation you said the ball will hit in the progress from this and this.
Yes.
And this.
Yes.
The ball will stick on the membrane, right?
Yes.
But I think the membrane will stretch by the ball at this part.
Stretch.
Yeah. It does stretch.
Yes,
right?
that's what causes tension.
And if there some something like friction or something very close, and I think it will definitely stick on it. It will.
Oh, you mean that? When the ball goes out and it goes up, it will actually like so when it goes out and after it comes to this end point, it will actually change to this point and it's still on it. Something like that.
Yeah.
But so we didn't consider this because we did not observe that the membrane will be sticky like enough like.
Just because of the friction or something like that.
But why would the friction continue to come up? Because can you draw a force diagram like how? Why would the membrane come up? Because
like at this condition, the step is more right, and then when you ball goes up, and because of friction, and it will depend to the movement of the ball. So. I think the membrane will stick on it.
okay.
So, and I think if this phenomenon that exists, it will cause a horizontal wave on the membrane. So I think you should analyze all this.
Oh, but what I believe is it will become this, but once the ball leaves it, so once it becomes a little bit off the membrane, and since the membrane is vibrating so fast, it's it's a lot faster than the contact time of the ball. So I believe that the memory itself, even if it is slightly affected, it will still continue its vibration. And actually, we are drawing a bit exaggerate the motion. So actually, if the memory is a straight line, it's only vibrating like this. So it's actually very, very small. Yeah. It's not like it's something like this. Yeah. So we're a bit over exaggerating.
But there is some horizontal force.
Yes, but I think it will be too minor to or too minor to
But you can approve it, like you didn't conduct experiment.
Yes, we didn't consider.
Yeah.
Do you have a better? Do you have a way that we can measure the wave created by this?
I think you can just push the ball into the membrane and take it up. And you will hear a sound.
But wouldn't
I
that?
think that will.
I did do that.
Oh yeah.
For fun. But what I realized is exactly like this. So if I put the ball down and I put it out very, very fast, and there is a sound, but if I put it out very, very slow, and the membrane isn't vibrating, if I like this and then I put it up very, very slow, there would be a sound, and I wouldn't find anything sticking to the ball. So I believe in our it's more like a fast motion, right? So it's coming down and coming up fastly. But so I believe
but your hand won't fast as the vibration.
Yes, but of course, and so the sound is not as clear too. So
but you can say that you can just say that the vibration just cut your face motion of your hand, right?
No, but like what I'm trying to tell you is if I pull the ball fast enough, I believe that is a similar phenomenon to when a ball drops. Yes.
Okay. So and for my the other suggestion, I think you should analyze the like something like resonance, because the air in the container will, I think it will strengthen the frequency of your sound.
Do you mean like because the memory pushes down, so there is do you mean so because the image, so there's a container, and because the memory pushes down, so the air pressure here will be compressed, and do you mean this?
I think there has some resonance. I think you should analyze it.
Oh yes,
because
so
the presentation is lack of the.
So do you think we should collect the data, for example, put a microphone inside and outside and see what, or
you can just try to use different size of container to to ensure that
yes,
different
yes, that's a good point.
Yes,
that's a good point.
Okay. So okay, I think I finished the discussion.
Right, so the opponent summarized the discussion 1 minute.
So I asked the reporter about the method to measure tension, and he said I think he didn't exactly measure the value of the tension, and I think if the reporter can do this, I think the presentation will be more nice. Okay, so and I asked about the frequency spectrum, and they didn't have any data on this. And we discussed the vibration from chamber, and we think the the plastic top is so and the thickness is so hard to move, so hard to vibrate. And about the horizontal wave top, I think we disagree with them.
Questions of the reviewer for the reporter and the opponent, and answers to the questions. 3 minutes.
Okay, first of all, I want to ask reporter, what do you think is the original for the sound?
Origin of the sound.
Yes.
The first sound would be when the ball touches the membrane. However, after that, but it's only a minor portion of the whole sound, and it also is a membrane vibrating.
The same question.
Okay, I think there are two results. I think for two sources of sound. One is the vibrating membrane, one is chamber. Okay.
In your presentation, page 9, you mentioned equation, but I don't see the. Do you agree to? I want to ask opponent. Do you agree to the reporter assume the membrane to the spring motion?
I think actually not really good because the springs case it's not the same.
Can you explain or prove that why you want to use it?
Yes. So if the membrane was to change from here to here and then to here, I agree that the tension will vary. And then if we assume it as a K constant, it would not be okay for us to assume it as a K constant. However, it's actually like this. So it's very, very small. So I think the tension would not vary from like that much.
Okay.
Yes, so
in your page 14, you mentioned equation.
here.
You say that there is no drag force, but then I don't see the relationship between the experiments and these equations.
Yes.
What is the main focus you use to explain this equation?
Okay, so if there was drag force, which I did show the derivation, if there was drag force, we would add some correctives to this amplitude. But however, this two, V0 and omega will still be the major impact of it. So as long as we know what will increase if the volume increase. Yes, so
you did
that's
contact for your experiment.
Yes, we did. So in our experiment, everything, height varied, this is the frequency, volume, and we can know that because here.
Thank you. And last one I want to ask is, how do you consider the correctly time you sketch for your experiment data?
Sorry?
The frequency.
Time's up. Declaration of the reviewer. 2 minutes. The reviewer takes the floor.
Okay,
4
so
minutes.
I'm the reviewer today, and today's problem is number 14, pour on membrane. Okay, so I think the problem statement tells us to find the original sound and the relevant parameter. So, and then it's the summary and the comment of the report. So the reporters first start at his theory and the sound and origin of the sound and two types of the dynamic model and the frequency of the sound and the volume of the sound damping. And for his variables, he chooses drop height of the ball and the mass of the ball and tension of the membrane. So for his conclusions, these variables increase the results of the frequency and the volume. So for his advantage, first of all is the complete theoretical analysis and fourth of theory, and the third is the good setup. And for the suggestions is lack of conclusions and lack of experiment data, put more experiment video, and for it didn't plot error bar, and five is large deviation between the experiment data and the theory. So and here's the summary and comment of the opponent. And the opponents first start at the summary, and that is the strength and suggestion, and that is the questions for discussion. So for the advantage to the opponent is clear question, and the suggestion is discuss more about the question of the theory and discuss more about the experiment data, and cannot catch the key point of the problem and keep asking trivial and technical questions. And okay, so here's the summary and comments of the discussion. And first, the question is, how did you measure the tension? And reporter says that I didn't measure it, but I used new membranes in each experiment. But I think that the membrane tension needs to be calculated because the phenomena has a great relation to the membranes. And next is, did you consider the membrane's horizontal forces? Reporter said that we didn't consider about it. I think the problem statement didn't tell us to measure the forces causing, but it's a great opinion for opponent, so I think the reporter can consider that in the future. So here's my questions. First of all is, what is the original sound for the, I didn't see that in his opponent's question, so. In my opinion, I think it's the vibration of the air inside the container. And reporter says that he thinks he has two sources about the vibration, and opponent think that he has only one source. And next is is there any relationship between the sound and the frequency bouncing? But I didn't ask in the discussion, but I think it's the bouncing makes the membranes vibrate and then affect the air inside the membrane. So, and my question 3 is, which time did you choose for measure the sound? But I didn't ask in the discussion, but I didn't see that the clear explanation for which time you measure to analyze. I want to know what is the correctly time you get from the data. So that's my presentation. Thank you.
Conclusion remarks of the reporter, 2 minutes.
So in our discussion, first with the opponent, they mentioned that the member will stick to the ball, although the member is on the bad side, and then they believe that there will be some horizontal waves because of friction affecting it, and we should consider that. And then they said that we should consider the resonance of the container, and we agree this one. But however, for the sticking part, we believe that is not as relevant, and they both believe that we can't use a spring. But first of all, they didn't say why we can't use a spring, and we believe that our assumption is reasonable. And next one. So for the summary of the reviewer, the reviewer asked why the membrane can be seen as a swing, and that is because the amplitude is small enough to neglect the tension or the K changing. So the tension will change, but we can we can see it as a linear chain to the k, like that, just like a chain, just like a string, which is k, and f equals to kx, and tangent of the and they say that we have to quantify the measure the tangent, and our tangent parameter is we just want to compare the difference between how higher tensions or small tensions will affect the frequency and the volume. But we do agree that a better way to test tension will be the Dane test pen. Yes, and that will be my concluding remarks. Thank you.
Okay, so now it's time for questions of the jury.
So we all know that the membrane is doing a two-dimensional motion, and obviously you simplify that into one-dimensional, like a spring. You simplify the 2D motion to the one dimension. What makes you think this simplification is justified? And the second question, a very short one, do you think there is a standing wave for the sound or not?
Standing wave for the sound. I believe, so let's answer the first question first. So I think, because the reason why this assumption, besides the amplitude I was talking about, is because that our classical is actually circular, so it's symmetrical. It's pretty symmetrical, and we think that we can cancel out the horizontal components. Yes.
There are more than one mode. The mode is not just one mode. For the 2D, the membrane will.
And I think the classical dissolution of the 2D dimension is based on function, but I think they have a lot of I think a lot of points to discuss. So I didn't mention to.
I think you mentioned that this standing wave. I think in the container, I think the wave for the sound is standing wave.
It is. Okay, thank you.
For the reporter, can you show your fast Fourier transform, the graph, your FFT?
Graph? On the PowerPoint?
Which page?
Okay.
That's your. I want to also ask your question about that.
Sorry?
Thank you. The fast Fourier transform. FFT plot.
Yes.
You see like the frequency plot. Can you show that?
On page 9. Sorry. This one?
Yes. Okay, so there's the horizontal is the frequency, right?
Yes.
So there's a lot of frequency. So which frequency you pick when you later your analysis of data? So which peak you pick?
Which people?
The frequency. Okay.
So this is only a demonstration of the.
This is not your result.
No.
So
no,
you do the fast Fourier transform. So I saw your plot in the graph.
Yes. So we use the average of the first 5 bounds. Is that what you're asking?
So I mean the original data. So
original data.
You got the sum. You recall the sum. You can take a Fourier transform.
Yes.
So what's that?
You
Do
mean
you
Additional data.
no?
No. It's on a PowerPoint and we don't have the data right now. It's on our seniors computer. We use our seniors computer and Google.
Okay. So how about opponent? Do you think you also do this experiment, right? You recall the sum. Do you take a Fourier transform to
Yeah.
see the frequency?
Yeah.
Yes. What do you think?
And I think the spectrum of Fourier transform is very complicated. It includes a lot of frequency peak, include the sound of environmental, come from environmental, and the membrane. It has a lot of frequency.
In my opinion, I think the highest frequency is that our experiment want to choose for the data.
So you have seen this data. Do you do this?
Yes.
So you have seen this result.
Yes, we see these results. So we consider to the highest peak to
the highest peak is your frequency.
Yes.
So my question is after this, if you want to change if you want to see the highest frequency, moving up or moving down, what did you do?
For me, I only consider the first drop for the metal ball. So there's only a wave so I can consider that the wave highest to transform to the magnetic.
Okay, so jury, please mark your grades. Right, so jury, please give your grades for reporter. All right, so next, please give grades for the opponent. So 6, 5, 5, 6, 5. So finally, we give grades for reviewer. 6, 7, 6, 7, 6. Okay. Thank you. Now we have